I wanted to do a demonstration in Excel to help you understand the ideas of the MAD, variance, and standard deviation, and why they all increase when the data has more dispersion. First, I need to explain everything that's on the screen right here. I created an Excel file, and in this column over here, I created a made-up set of data values. And let's pretend that these data values are the exam scores of 20 students who are in a class. So we're pretending that there's 20 students who are taking a class together, and these are their 20 exam scores. Over here, we can see their 20 exam scores in a graph. This graph right here is actually, it's like a histogram, but it's actually called a dot plot. And I'll explain how a dot plot is different from a histogram. A histogram has a bar above each value that shows how many times that value appeared. For example, if the bar goes up to the second tick mark, that means that the value appeared 2 times. In a dot plot, it plots a dot above the value each time that value appears. So if a value only appears 1 time, it has 1 dot above it. If a value appears 2 times, it has 2 dots above it. So here's a value that appeared once, and here's a value that appeared 2 times. And if a value appeared 3 times, there would be 3 dots above that value. But in my data set, each value only appeared once or twice. And a dot plot shows the shape of the data just like a histogram does, because when a value appears a large number of times, it has a large number of dots above it. And the dots go up high. But if a value hasn't appeared very often, it doesn't have very many dots above it, and the values don't go up as high. So just like a histogram, a dot plot peaks where most of the data values are, and then it trails off when you have less and less data values. So now I'm going to explain these other columns over here. What I did first was I calculated the mean of the data in Excel. Excel was able to give me the mean of the 22 exam scores. It just added them and divided the total by 22. So the mean exam score is 80.8. If we look at this graph right here, we can see that it makes sense that the mean would be 80.8 because 80.8 is about at the center of the exam scores. Remember that the mean is typically somewhere near the center of the data. It's not always exactly at the center of the data, but it's usually somewhere near the center, unless the data happens to be highly skewed. If the data is highly skewed, then the mean will be pulled out far in one direction or the other. What I did next was I put the mean of 80.8 in all of these cells right here, and then in each row I subtracted the data value by the mean to get a deviation. So 65 minus 80.8 equals this deviation right here. 68 minus 80.8 is equal to this deviation right here. Remember that when you subtract the data value by the mean, you get a deviation. So each person has a data value and each person has a deviation. If you take off the negative signs, you get a column of absolute deviations. So what I did over here was I just created a column of absolute deviations, which it just left off all of the negative signs. And I'll remind you about what a deviation shows and what an absolute deviation shows. I'll remind you about what they tell you. So remember that the deviation of a data value tells you how far the data value is below the mean or above the mean, and a deviation is negative if the data value is below the mean, and a deviation is positive if the data value is above the mean. So this value right here of 65 is our lowest value down here, and it's below the mean. which is why the deviation is negative. And what this deviation of negative 15.8 is telling us is that the distance from this data value of 65 to the mean up here is a distance of 15.8. And this absolute deviation right here is also telling us that the distance from the data value of 65 up to the mean is a distance of 15.8. The only difference between the deviation and the absolute deviation is that the absolute deviation leaves off the negative sign. The absolute deviation doesn't tell you if the value is below or above the mean. The absolute deviation just tells you the distance from the data value to the mean. Let's now look at this data value of 92 right here. It has a deviation of positive 11.2. Since the deviation is a positive number, it means that the value is above the mean. And it's true that 92 is above the mean. So 92 is our highest value up here. This deviation of 11.2 is telling us that the distance from 92 down to the mean is a distance of 11.2. Right here, this is a distance of 11.2. The absolute deviation is telling us the same thing, that it just doesn't have a sign in front. The absolute deviation doesn't tell us if the value is below or above the mean. Now what about this value right here, 84? It has a deviation of positive 3.2. So that's telling us that the distance from 84, which is about right here, to the mean is a distance of 3.2. The absolute deviation tells us the same thing, it doesn't have a sign in front. The absolute deviation doesn't tell us if the value is below or above the mean. So like I said, this is a distance of 3.2 from the value of 84 down to the mean. So this column right here of absolute deviations tells us the distance from each individual data value to the mean. Each of these data values over here has an absolute deviation that says how far that specific data value is from the mean. And we can see that these absolute deviations aren't always the same number because some values are closer to the mean than others. These data values down here have big absolute deviations because they're far away from the mean. I think this one is 15.8 from the mean, and this one right here is 12.8 from the mean. So these values are far from the mean, so they have big deviations. These values out here also have big deviations because they're far from the mean. And these values that are in the center have smaller absolute deviations because they're closer to the mean. So like I said, the absolute deviations aren't all the same because some data values are closer to the mean than others. However, the average or the mean of all of the absolute deviations is 6.74. What I did was I used Excel to calculate the mean of all of these absolute deviations, and the mean came out to 6.74. Excel just added these 22 numbers and divided the total by 22. So this number right here is our MAD because it's the mean of all of the absolute deviations. So what this is telling us is that even though the absolute deviations aren't all the same because some values are closer to the mean than others, the average distance to the mean is 6.74. So now let's see what happens to the MAD right here if we change one of these data values and move it further away from the mean. For example, what if we take 65 and change it to 55? Well, you can probably guess that this absolute deviation is going to change because if the data value moves further from the mean, the absolute deviation goes up. So let's watch it change. Well, now, instead of being only 15 below the mean, this value, which we see right here, is now 25 below the mean. The distance from this value up to the mean is now a distance of 25. Since this absolute deviation went up from 15 to 25, the MAD, or the mean of the absolute deviations, went up, because if one of the absolute deviations goes up, then that causes the mean of the column to go up. So the MAD has to go up. Now what if and I also want to make it clear that the MAD isn't just affected by the lowest and highest values. It's also affected by the values. It's also affected by all of the other values. So to make that clear, I'll take a value that's somewhere in the middle of the data, like this value right here of 71, and I'll move it further from the mean. And I'll show you that that'll affect the MAD as well. Maybe I'll drop 71 down to 61, and I'll show you what happens. Well, you can probably guess that when this value drops to 61, that this absolute deviation of 9.3 is going to get bigger, because this is just the distance from the value to the mean. And if the value moves further away from the mean, the distance goes up. So now, let's change it to 61. And we're going to see the value move to the left in our graph. So now it's moved out there. And now, this value, which we see right here now, is now 18.8 away from the mean. So since this absolute deviation went up, the MAD went up, because if this absolute deviation goes up, the mean of the column goes up. Now let's take maybe this value right here, which is 80, and move it further away from the mean. Maybe let's move it down to 73. So right now, this value of 80, which we see right here, is really close to the mean. It's only 0.2 away. But if we change it to 71, or maybe let's say 73, that value is now further away from the mean. It's now 6.45 away. And since this value moved further away from the mean, its absolute deviation went up, and that caused the mean of the absolute deviations to go up. So now our MAD has increased. So every time I move a value further away from the mean, the absolute deviation goes up. Every time I move a value further away from the mean, the absolute deviation of that specific value goes up, and then that causes the MAD to go up. Now I'll just play around with this a little bit more. This value right here is 73. Maybe I'll move it down to 57. So it moved further away from the mean. We just saw it move. We just saw that dot move further away from the center, which means that the absolute deviation of that value went up, and then the MAD went up as well. If I take a value and I move it really far away from the mean, that's going to have a big effect on the MAD. For example, if I take this 55 and move it down to 15, this value is now an outlier, and it's, well, 61.65 away from the mean. This is the distance from this value to the mean of the center is now a distance of 61.25. It's a big distance. That's why the MAD is so big. I'm sorry, that's why the absolute deviation of that value is such a big number. Since this absolute deviation went up by so much, it had a big effect on the MAD. The MAD went up from about 9 to about 11.72. Now let me bring that value back to where it used to be. Now the MAD went back down to 9.32. So I hope you get the idea that each time a value moves further away from the mean, the absolute deviation of that value goes up, and then that causes the MAD to go up, because the MAD is just the mean of the absolute deviations. Now I'll explain the variance and standard deviation and how they're affected by the dispersion. What I can do here is I can multiply each deviation by itself. I can square each deviation. So this is just the deviation multiplied by itself. And this will do it for every row. The variance is just the average of the squared deviations. So this is our variance right here. I'll give it a color, maybe orange, or maybe I'll put it in green. And then the square root of the variance is our standard deviation. So this is our standard deviation. It's just the square root of the variance right here. Now let's move a value further away from the mean, and let's watch all three values go up. So I'm going to take this value right here of 81 and move it further away from the mean of 78. So maybe I move it up to, let's say, 95. So, okay, so this value is now further away from the mean than it used to be. It's now 15 away from the mean, or 15.65. It used to be only, well, it used to be only 2.35 away. It used to be really close to the mean. But now, since I changed it, it's now 15.65 away from the mean. And when I move a number further away from the mean, like I did here, what happens is that the absolute deviation goes up, like I just showed you. It went up from 2.35 to 15.65. When the absolute deviation goes up, the squared deviation goes up also. Let's take a look. When the absolute deviation was 2.35, the squared deviation was 5.5. But when the absolute deviation went up to 15.65, the squared deviation went all the way up to 244. So when a value moves further from the mean, what happens is the absolute deviation of the value goes up, and then that also causes the squared deviation of that value to go up. When the squared deviation of the value goes up, that raises the mean of the squared deviations down here, which is our variance. So the fact that this squared deviation went up from 5.2, 5.5 up to 244 meant that our variance went up right here. And when the variance goes up, the standard deviation goes up along with it, because the standard deviation comes right from the variance. So the point I'm trying to make here is that when a value moves further away from the mean, like this one did, the absolute deviation, or the distance to the mean, goes up, and the squared deviation goes up also. When a value moves further from the mean, like this value did, the absolute deviation of the value goes up, and the squared deviation of the value also goes up. The fact that the absolute deviation goes up means that the MAD increases, and the fact that the squared deviation goes up means that the variance increases. And when the variance increases, the standard deviation has to go up along with it. Let's do one more example. What if I change this from 55 to 25? Well, this value is now much further from the mean. It's much further below the mean. It's now, this value down here is now 52.85 away from the mean over here. It's a big distance. So since the value moved further from the mean, the absolute deviation of the value went up. And because the absolute deviation went up, the squared deviation went up also. And when the absolute deviation goes up, the MAD goes up. When the squared deviation goes up, the variance goes up. And when the variance goes up, the standard deviation goes up also.